Hi, Chem 110H, Dr. Bevilacqua here with just a quick review on the difference between vectors and scalars. Vectors are quantities that have both direction and magnitude, whereas scalars just have magnitude. So let me give you a few examples. Certainly an important one for vector is velocity, and its counterpart as a scalar would be speed. So when we do velocity, we might put it v and put an arrowhead over it like that. And for speed, you know, if we used v, we do this, or we use s for speed, and it's just the amount. So in other words, when I think about a vector, I have to think about a coordinate system, and if I have an x, y, z coordinate system, then I can have a velocity, say like that, which is along the y-axis. But I could also have velocity going this way along the y-axis, another one, v sub y prime. And if I added these two together, they would sum to 0. And how do I know that? Well, you can sort of see that they oppose each other. But what we often do is we take these and we put them down on an axis, a coordinate system. So if I take this first guy and I add them head to tail, and I put v sub y like that, here is the head and here is the tail. So then I'll take this guy and I'll put its head on this guy's tail. That's what it means to add them head to tail. So now I'll go ahead and put v sub y prime back, and you can see I'm back to where I started, and so their sum is 0. If I were to add together these two speeds, they would not add to 0 because it's just the magnitude. Another place where you see vectors and scalars has to do with dipoles. Dipoles are vectors, and dipoles are equal to charge times separation and distance, whereas charge itself is a scalar and distance is a scalar. So the dipole has directionality to it. Let me give you an example. If I take a molecule like, let's say, water, and this it's bent, this angle turns out to be a little bit less than 109, let's say about 107 degrees. And of course there's a dipole. There is charge development on this bond right here, and that charge is delta plus on the hydrogen, delta minus on the oxygen, because the oxygen is more electronegative. And so we'll often go ahead and write the dipole like that, where the plus is the delta plus and it points toward delta minus. We inspect each and every bond. Let's look at this OH bond, and we'll draw its dipole like that. Let's give these numbers. We'll call this dipole 1 and this dipole 2. Now we can go ahead and add these together, and we'll take a coordinate system, and I'll take first dipole 1 and I'll drop it right here at the origin, like so. And then I'll take dipole 2 and I'll drop it here, and again I'm going to add it head to tail. I'm going to put this tail right there. This was 1. Here comes 2. Like that. And now I'm done. What is their sum? Well, let me do their sum in another color. I'll do it in red. And the sum is from where we started to where we ended. And so it goes like this. It goes from the start of 1 to the finish of 2. That is the total dipole. And if I take this, you can see if I take this and I draw it up here in red again, it kind of makes sense, right? Because 1 is pulling this way a little bit, 2 is pulling that way a little bit. If you imagined, you know, you tied a rope here and a rope here and you pulled on both of them, the net direction would be in that direction. And so dipoles definitely have directionality, and we can think of them as vectors. Thanks for listening.